Welcome back to 2FA3, Discrete Mathematics with Applications 2 at McMaster University. This is McMaster University again. In the previous video, we talked about theory of computation, different computational models, their corresponding grammars and languages, and then we started to talk about strings and the operations we can perform on strings. In this video, we continue with decision problems. As I said in the previous video, automaton could be used as acceptors or transducers. An acceptor has an input tape where it reads a string from and tells us if that string belongs to the language that the automaton accepts or not. Transducers, on the other hand, have an output tape and produce a different string, which is the same word in another language, or they perform some computation on the input and put it on the output tape. But we are not focusing on transducers and will work with acceptors in this video, which reflect the nature of decision problem. A decision problem is essentially what we just said for acceptors. They receive an input and provide a Boolean answer, yes or no, true or false, 0 or 1 for it. An example of a decision problem is a certain formula closed or not, with respect to a certain alphabet? A solution to a decision problem is basically an algorithm that finds that yes or no answer. And when there is an algorithm as a solution for a problem, then we say that its solution is actually a computable function. Computability and decidability were trendy research topics in 1930s, and geniuses like Church and Turing used to work on them. In a nutshell, what they concluded is that a decision problem is decidable if there is a Turing machine that computes its solution, and for each input it terminates and produces a correct output. Otherwise, it is either semi-decidable or not decidable. We will talk about this a little bit later when we have a better idea of how Turing machines work and what recursive languages are. But for now, we work with finite automata and regular languages, which are subsets of those two. For now, just understanding the decision problem and how it is formalized as a question of strings and languages could help us better understand how finite state automaton work and that it can resolve any problem that is reducible to the decision problem over strings. So the formalized version of a decision problem is described as whether a certain string is a member of a language defined with sigma as its alphabet, an arbitrary set, or a subset of sigma star. A solution to this problem is a computable function which maps any string to a yes or no answer. And the answer is yes, only if the string is indeed a member of a set or language S. Automata resolves problems defined as such, or problems that we can describe with this form. For example, assume that we have a theory defined in a logic language which has a certain signature and alphabet, and we want to see if certain formulae are valid in this theory. We reformulate the problem as decision problem over strings. We say that every formula in T could be considered as a string made of symbols defined in sigma, and S is a set of all the strings that represent valid formulae in T. Now, a formula is valid in T only if its corresponding string is a member of S. This was only an example. There are many other problems that could be resolved by finite automata once we reduce them to a decision problem over strings. And that is why finite automata is the underlying basis of modern computers. So let's talk about finite automata. We have two types of computational models in general, deterministic and non-deterministic. We start by deterministic finite automata, and then we'll talk about non-determinism later on. Finite automata is the most basic version of finite state transition systems that consist of a number of states and transitions between those states that are triggered by symbols from the input. So we can represent a finite automata as something like this. So it has an input tape, and then a starting state, and then several other states. So this is Q0, for example. And then from the input, they read certain symbols one by one. So first they read this one, and assume that we have a loop, and assume that sigma here is only A. So, or maybe also B, and then with B it goes somewhere else. So we first read the first symbol of the input, which is A, and that triggers this transition. Then the second symbol, another A. So again, this one is triggered. And then we have another one, which is B, which triggers this one. So we read one by one anything which is on the input tape, and then accordingly take the proper transition. And once we are done with reading the input, if we find ourselves in a final state or accepting state, then the string is accepted and it is a part of the language that this automaton accepts. Otherwise, if this is not a final state, then the string is not accepted. A more formal definition is a tuple that identifies an automata by its set of states. So again, let me highlight things. This is a set of states that is for sure a finite set. The alphabet of its inputs, a transition function that defines movements between states based on what is on the input tape, the starting state, and a set of final states. We can have one final state or a set of them. The transition function defines one step moves from one state to another, but extended transition function, which is represented by delta cap, is like a sequence of those transitions, starting from the starting state to any state in the automata with more than only one transition. We can visualize a deterministic finite automata, or DFA, or as it is also called, a finite state automata, FSA, with a table or a diagram. So now let's see an example. So this is an example of a DFA, which is represented by a table. So we have a set of states, and here we have the inputs that we read from the input tape, and here we define transitions. So, and then we have one starting state and two final states. So what the table is saying is that if we are in the first state, Q0, by reading an A from the input tape, we will stay in Q0. Otherwise, if we read a B, then we will go to Q1. If we find ourselves in Q1, reading A from the input tape, we will move to Q2. Otherwise, if we read a B, we will move to Q3. And then the same thing for Q2 and Q3. So if we are in Q2 and the input we are processing is not done yet, so it's not fully processed, there are still symbols that we haven't read, then we exit from the final state. So that doesn't mean that the word is accepted. If we meet the final state once, or we pass by it once, it doesn't mean that the word is accepted. So we need to be in final state when the input is fully processed. So if we are in Q2, which is a final state, but the word is still half not read from the input, then we go on. We continue with A and B, and the same thing for Q3. This is basically the definition of a DFA. But a different representation of the same thing, which is probably more intuitive, is the diagram. So this is the same thing, where each transition in the table is represented by an arrow between two states. So let's just evaluate this automaton and see what is the language that it actually accepts. So usually starting from the start state. Oh, and this is the notation with which we define a start state. So that tells us where to start. And usually starting from here, we can start to describe the language that the automata accepts. So here, any possible string, any potential string would start by a sequence of A's, or it could start with a B. But anyhow, it needs to have a B in order to move out of Q0. So we have a B, but we could also have a possible sequence or string of A's before that. And then again, we can have a bunch of A and B's, and with an A, we can go back and create the same thing again. So the first part of this language is a little bit arbitrary. There is no specific pattern that we can define here. And actually for this particular automaton, it's easier to start from backwards, so from the final states, which is usually not the case, but for this one it is. So let's see when we end up in Q2. So as you can see, there are two transitions that take us to Q2, and both of them are triggered by reading A from the input. So the words that are accepted in Q2 end with A. But then both of them are coming from, one is coming from Q1 and one is coming from Q3. And the only way to enter Q1 is actually having a B. So before this A, we most certainly had a B in the word. And then before those, we could have any arbitrary combination of A and B. Let's see what is the string that is accepted in Q3. So the only transition that actually takes us to Q3 is this one, which is a B. And then we can have any number of B's again here. So if a word ends in Q3, it ends with B, and then maybe some potential repetitions of B. And the only state that we can be in before moving to Q3 is Q1. And again, the only way to be in Q1 is to have read a B before that. And then again, we can have any combination of A and B before that. So these are two types or two patterns of strings that are acceptable by this automaton. And the similarity between the two is that actually the next to last symbol in both patterns is a B. So the general format of the word which is accepted, or strings that are acceptable by this automaton, are some sort of combination of A and B, and then B, and then it ends by an A or a B. And the shortest example is that we start by, we read B from Q0 and then A, and we end up in Q2, so B, A. Or we read a B and then another B, so B, B. So two shortest acceptable strings are BA and BB. So let's see the formal definition of being accepted, a string being accepted or rejected by an automata called M here. So a string X defined over certain alphabet is accepted by automata M if some extended transition from starting state, reading the input, takes it to a final state. Otherwise, if we never reach a final state reading the elements of the input, then it is rejected. The set or language accepted by automata M is denoted by this one, LM, and is the set of all strings accepted by M. So the definition is that all those strings that are defined over the alphabet, and there is some extended transition that reads them and take the automata from a starting state to a final state. And then a set is a regular set or a regular language if it is equal to the accepting language of an automaton. So, for example, the language of the automata we've just seen in the previous slide is all words defined with alphabet A and B, such that their second to last symbol is a B. And then now we will see another example where the number of zeros and ones are equal and is actually even. We'll see this example in a second. Then we'll say two deterministic finite automatas are equivalent if they accept the same language. So when we are thinking of the same language, we might define DFAs with maybe different numbers of states. We might define transitions differently. So there could be different implementations of a deterministic finite automata that accepts a certain language. And those two are basically, even if their implementation is different, they are equivalent because they accept the same language. So this is the example where the automata that accepts the language where the number of A and zeros are equal and is an even number. We have four states. We can define four states and assign meanings to those states. We can say that Q0 is the state in which the numbers of zeros and ones that we've read up to now from the input are equal and are even. Q1 is when we have an odd number of ones but even number of zeros. Q2 is when we have an odd number of zeros but even number of ones. And Q3 is when we have an even number of both of them, right? So we have four states, each representing a different situation where we could be in by reading different symbols from the input. And then the other thing that you need to note is that the start state is basically also the final state. And the thing is that the definition of language here says that the number of zeros and ones are equal and are even, and 0 is even. So if we have no 0 and no 1, which means empty string, it confirms with the definition of LM2, so it is acceptable. So when we are in the starting state, if there's nothing to read from the input, it is already accepted, right? Otherwise, if we are in Q0, it means that for now we have, up to now we had equal numbers and even numbers of zeros and ones. Now if I read 0, that means that now I have even number of zeros and odd number of zeros and even number of ones, and that takes me to the definition of Q2. Q2 is when zeros are not okay. But if I'm in Q0 and I read 1, now it means that I have even number of ones, and that takes me to Q1. So I define Q1 as being the state in which ones are odd. And then if I'm here in Q1, so I have odd number of ones, if I read 0, that takes me to Q3, where both ones and zeros are odd. But if I have already an odd number of ones and I read one more 1, that means that now I have even number of ones, and that takes me back to Q0. If I'm in Q2, means I have odd number of zeros. If I read one other 0, now I have even zeros, and that takes me back to Q0. If I read a 1, that means that now I have odd number of zeros and ones both, so I go to Q3. And here in Q3, again, if I read 0 or if I read 1, that means that one of them becomes even, the other one is still odd, so that takes me either to Q1 or Q2. So assigning some kind of definition or some kind of concrete state to each of the states of transition machine could help you define this table. But it is again probably easier to do that with a diagram. So this diagram, we have again a start state, which is also a final state, and that says, so whenever I exit from this state with a 1, then I can come back also with a 1. So for each 1 that I read, I do not come back to the final state until I read another 1. And that makes it an even number, an equal number of 1s. And then the same thing for zeros. The same thing again because we want to analyze different combinations of 1s and zeros. So we want to be able to read something like 1 0 1 0, but also something like 1 1 0 0. So if we have 1 1 0 0, these two transitions cover the first part, and then these two transitions cover the second part. But if we didn't have this half of automata, we could not process this one. So this one takes 1, then 0, then 1, then 0. So in order to cover every possible combination of 1s and 0s, we needed to have 4 states. And in one of them, we have odd number of 1s and even number of 0s. In this one, again, we have odd numbers 1 and 0s both. Here we have even number of 1s, but odd number of 0s. And then Q0 again is the acceptable or final state where I have even number of both 0s and 1s. So we stop here with these two examples, and in the next video we will talk about non-deterministic finite automata.